We'll continue what we have discussed last week, regarding biosensor. So we have discussed about the components of biosensor. Then we have also discussed about the different ways of immobilization, of the biomolecules into the substrate, of the into the surface of the transducer, the physical transducer element. Yeah. The four possible ways can be membrane entrapment, physical adsorption, matrix entrapment, and covalent bonding. And we have discussed last week also on the advantages and disadvantages of each of these immobilization methods. Some methods will give you the correct orientation of the biomolecules, especially the covalent bonding. However, of course, then it will require special chemistry to bind the biomolecules to the surface of the transducer. The surface of the transducer needs to be treated first, with certain chemistry, and usually you will need also a linking mechanism, a chemical linker to link between the chemical on the surface of the transducer with the chemical on the biomolecule itself. For protein or like antibody, usually they have the amino and NH amino functional group, which can be exploited to bind with specific chemistry, amino specific chemistry, to bind it onto the surface of the sensor of the transducer. That is why with covalent bonding, while it can provide the almost perfect interaction between the biomolecule and the analyte, but it requires this special chemistry, multiple steps, so it is a bit tedious and of course costly because you require additional chemistry. And we have other methods which is less costly, like using porous encapsulation or matrix, like using hydrogel, and as well as other material that can where the biomolecules can find their way or can be stuck in the porous structure of the matrix. Of course, then the orientation will not be as ordered as in the covalent bonding. However, if you have enough space, enough thickness with enough porous structure within that matrix, then relatively you will have a good interaction between the biomolecules and the analyte. Then we have membrane type of immobilization where the biomolecules is being contained within the membrane, and the membrane will only permeate the analyte of interest into the space between the membrane and the sensor, where the analyte can then interact with the biomolecule, and the biomolecule cannot escape to outside. Then finally, we have physical addition by physical absorption. This one to be the physical absorption, where the biomolecule is just being attached physically through physical adherence, which is based on electrostatic binding or van der Waals or hydrogen bonding, this kind of non-permanent chemical binding. This is the cheapest among the four, but of course then usually the orientation will also be random. The orientation of how the molecule is standing on the surface of that sensor will also be random, but it can still have some interaction. Okay, so these are some of the parameters or fabrication criteria which you need to also to pay attention to when you are designing biosensor. Okay, then we have discussed also last week about the common bioreceptor component. We have discussed about enzyme, antibodies and antigens, nucleic acids, cellular structure or whole cells, and other biomimetic receptors. And then they all can be divided into two types of bioreceptor, which is either as catalytic, at the catalytic biomolecule, in which then the biosensor will be called as catalytic biosensor. And in this case, then the biomolecule will only catalyze a reaction between the analyte with certain other reagent and to produce a product. And during that reaction, some physical parameters will change. For example, if there is electron change, ionic exchange, and this ionic exchange can be captured or can be tapped using electrodes. And this includes enzyme as well as the whole cell microorganism, bacteria, for example, that contain the enzyme there, or even the whole issue, a slice of intact tissue, which contains various enzymes within it. So it depends on the biosensor that you design, whether you want to be very specific or you want to be maybe representing a more complex biochemistry which require multiple enzymes to be present there. If you want your biosensor to be specific, then usually we will just purify a single type or maybe two types of enzymes and attach it or immobilize it on the surface of the transducer. However, if you require a specific certain metabolism, like whole cell or tissue, then we can have the whole cell. Yeah, maybe then the interaction of the analyte will do several pathways, several steps of reaction with multiple enzymes within that whole cell or tissue. Yeah, it depends on what kind of application you are developing. So this is what makes biosensor actually flexible. So it depends on your application. You want to detect only specific molecule, or you want to detect, for example, toxicity to the whole organism or to the whole tissue. And in that case, then you can choose which biomolecules or molecule bioelement that you want to immobilize onto the physical transducer. Then we have also second type of bioreceptor, which is called as bioaffinity components, which depends on binding reaction between the bioelement with the analyte of interest. This include antibody and antigens and nucleic acids. Last week we have discussed about genosensor using DNA or RNA. And so this when affinity sensor binds, the transducer binds the biomolecule of interest, and upon binding, usually there will be heat, either being absorbed, or being dissipated, or otherwise some other reaction, photochemical reaction, where there will there will shine light due to chemical luminescence or phospholuminescence or other luminescence reaction. Otherwise, there might be, at least there will be some mass change. When antibodies, for example, and antigen bind, then the whole complex mass will be heavier than before the reaction. And this mass change can also be detected using some of the physical transducer that we have learned earlier, using QCM, surface acoustic wave, using surface plasmon resonance optical sensor, and many other sensor, electrochemical impedance spectroscopy also, etc. Similarly, with nucleic acids, the reaction between DNA single strand with its complementary sequence will generate double strand DNA, which will result in an increased mass. And this increased mass can also be detected using various physical transducer. Finally, that we have learned last week also about cellular cell, where we use the whole organism or specific cellular component like the receptor within that cell as a bioelement in our biosensor. Then a new developing subfield within biosensor is the development or the increased use of non-organic, well, we cannot say it bioelement, non-organic or biomimetic element. So these are made from non-biomolecule, but however they act or they function similarly to the biomolecules. For example, genetically engineered molecule or peptides, peptides, PNA, peptide nucleic acids, last week, which PNA, peptide, nucleic acid, which combine peptide. Peptide is basically the basic building structure of protein. Peptide, nucleic acid, yeah, something like that. And then we have also molecularly imprinted polymers, MIP, which can work similar or resembles the functions of antibody. Yeah. And then last week I mentioned about MOF, metallo-organic framework. Yeah, a structure, a complex three-dimensional structure, which is made from metal oxide or metal, yeah, and they will form a three-dimensional structure which looks similar. It can bind or function similar like an enzyme, for example. So maybe if you can Google nanozyme, nanozyme or nanoenzyme, this is made using that metal organic framework, MOF, using inorganic material to function similar or mimicking the work of an enzyme. Okay, then okay, so now we try to delve more detail, to go into more detail to each of this type of biosensor, catalytic biosensor and affinity biosensors. The first one, the most commonly used biological components is the catalytic biosensor, which is usually we use enzyme. Yeah, so yeah, and there is a wide range selection of enzyme that we can use. The most common one, yeah, for in biosensors world is glucose oxidase, because a glucose sensor is one of the earliest biosensor developed in the market, being developed and also marketed now. It is quite common that you can find glucose biosensor when you go to pharmaceuticals, to apotheke, to Dr. Watson or Guardian, like that. But you can also use instead microorganism, where, as I mentioned also earlier, if you need a detection that take advantage of complex enzyme system, and as well as the coenzyme, where multiple enzymes work together. So rather than you are purifying individual enzyme and then combining them yourself, why don't we use the whole microorganism that contains both enzyme, for example, or multiple enzyme even? Yeah, that will be more practical rather than having to purify individuals enzyme and then mix them. And even then we need to do optimization. And also then the drawback will then, if we do it ourselves, the condition that this enzyme work may not be similar to their natural environment, which is within a microorganism, for example. So that's why many people use this enzyme that are work within use the whole microorganism, the whole bacteria as the bioelement, to detect analyte of interest, which require the work of multiple complex enzyme system, or coenzyme. Let's see now some of the applications. So enzyme biosensors are the first among the biomolecules to be used, in commercial biosensors also. So basically enzymes are protein polypeptide structure whose catalyze specific chemical reaction in vivo. In vivo means in a living thing. They accelerate the rate of reaction of particular chemical structure without being consumed in the process. So that is why in the enzyme-based biosensor, usually they can be used reversibly, so they do not need to be they can work all the time. Yeah, this is in contrast with antibody. The moment antibody binds to the analyte, its antigen, then it's not easy to separate them. Then usually that biosensor has to be disposed. Yeah, for example, like a pregnancy test. The pregnancy test use antibody for the beta gonadotropin. The beta gonadotropin is the biomarker for pregnancy in the urine that is also secreted in urine. So that paper, yeah, the paper test, yeah, for pregnancy test, they have this antibody specific towards this beta gonadotropin. And that is why when it binds, it's not easy then to unbind them. Right? So what you do then, you have to dispose the sensor. You have to use new sensor if you want to do a new sensing. In catalytic biosensor, on the other hand, because the enzyme itself, is not consumed in the reaction. It can, after the substrate is reacting with the product, after the substrate reacting with the other reactant to make a product, then it will detach from the enzyme again. It will detach, and then the enzyme is standalone again. It's on itself again, and it can do another reaction with the substrate. Like this, yeah. Substrate binds first to the enzyme, making a substrate and enzyme complex, and then the substrate enzyme complex, then it will react with another substrate, making it easier to react due to this complex. Then the product, since it does not fit again to the key lock relationship with the enzyme, it will be released from the enzyme. So become, at the end of the day, it become product N plus enzyme. So without the enzyme catalyst, usually the reaction between the substrate and product will take longer time. So the enzyme function as a catalysis to make the reaction faster between the different substrates and reagents to make product. So at the end of the reaction, the enzyme can withstand on itself, can stand on itself, and can react with new substrate. It works reversibly. Okay. The difference with chemical catalyst here, enzyme demonstrate significantly greater level of substrate specificity because of constraint placed on the substrate molecule by the active site in the environment, involving factors such as molecular size, stereochemistry, polarity, functional group, and relative bonding energy. And this is something which cannot be very difficult to mimic actually until now. In the past, it is not easy to mimic the specificity of enzyme because of this molecular size is specific to the substrate. Stereochemistry also specific. Polarity also has different polarity within the enzyme. Functional group also very specific. That's why the enzyme glucose oxidase can only catalyze glucose, oxidation of glucose to become glucagon, and resulting in H2O2 as well. Lactase oxidase also specific to oxidizing lactate to become lactic acid. Okay, and with catalytic, with non-organic, with non-biomolecular catalytic chemical catalyst, it is not that easy to do such catalysis. This specificity and selectivity is one of the advantage of biosensor based on enzyme. However, then there are also some limit. The sensitivity of the enzyme is directly dependent on the maximum limiting affinity underlying enzyme substrate complication and the rate of subsequent transformation. And after being isolated and incorporated into the sensor system, the decrease in activity of enzyme can be minimized by suitable pH, temperature, and other environmental conditions. Okay, so this is something important. The sensitivity is dependent on the maximum limiting affinity and underlying the enzyme substrate complication and the rate of subsequent transformation. Usually, for example, the enzyme and the substrate reaction is governed by what we call as Michaelis-Menten law. Michaelis-Menten law. So if this is the concentration of the substrate, Then at the beginning, usually then it is very sensitive. Afterwards, then it will saturate. So that's why the sensitivity here is dependent on the maximum limiting affinity. So after if the concentration of the substance, substance is quite large, then usually then sensitivity will decrease. Okay, welcome, Ezra. So then sensitivity will decrease. Yeah, when the concentration of the substance is relatively still low, sensitivity is, remember the definition of sensitivity, yeah? Sensitivity is dy dx. Okay, so here you see that the slope here, dy dx, is decreasing. So sensitivity decreases when the concentration of the substrate increases because of the maximum limiting affinity. This is governed by the Michaelis method. Please Google later what is Michaelis-Menten law. Yeah, because when you make sensor by sensor, usually the graph will be like this, the calibration curve. And after being enzyme immobilization techniques can be many, can be adsorption, just simple adsorption, can be also cross-linking. This is more expensive, of course, but very good. Or covalent bonding. Covalent bonding directly bind the enzyme, some part of the enzyme onto the substrate of the sensor, of the transducer, or physical entrapment using matrix. Electrochemical polymerization and self-assembled monolayer. This is called as SAM. For example, if you have gold substrate, you can use thiol. Yes, thiol is sulfur base. Yeah, like this. So thiol, it usually will assemble at the gold surface automatically this to form what we call as self-assembled monolayer. Or otherwise, your enzyme, you do some genetic modification to contain sulfuric functional group, yeah, at some I forgot the amino acid that contains sulfur at some part, so that then it will bind, bind to the substrate automatically at that sulfur site. Yeah, this is if you use gold. Yeah, if you use gold. Yeah, this is what we call as self-assembled monolayer, SAM. Okay. If you use cross-linking, it means that you use, this could be silicon or gold, and you use a molecule linking like this, and then you make the enzyme floating at some distance from the surface. Yeah. It depends. So if your binding reaction between the enzyme and the substrate is in this part, for example, then it is quite okay for it to be attached directly to the substrate of the physical transducer. Otherwise, if it is too close, for example, it is here, then this binding between the enzyme and the substrate may hinder the motion of the enzyme, because when the enzyme binds to the substrate, yeah, to the reagent, basically there is a nanomechanical motion there. And to reduce that steric hindrance, we call it steric hindrance. What we can use is this cross-linking, cross-linker, so that then the enzyme is floating certain distance above the surface of the physical transducer. That's what we call as cross-linking. Okay, let's take a break for a while. Let's pause the recording. Okay, let's continue with the next session. Okay, so yeah, so this is how an enzyme sensor, yeah, the schematic of an enzyme sensor. So there is analyte, yeah, and then there is the element transducer. In this case, it is the enzyme. So enzyme is very specific. It is like lock and key mechanism. So if the analyte has circular shape like this, then it will bind only to the lock, where it has also the complementary dome shape structure with the same radius. Then upon binding, of course, there will be then recognition. And this recognition will then produce signal. In the case of enzyme, it could be in the form of electron exchange. When there is a substrate or analyte being oxidized or being reduced, then electron is being exchanged there. And this can be captured or detected using electrodes. That's why here enzyme is very specific towards only specific analyte. And as we see here from this reaction, governed by the Michaelis-Menten relationship, as I have mentioned earlier. The relationship between parameters of relevant enzyme are given by Michaelis-Menten analysis. In Michaelis-Menten, so enzyme will react with the substrate, with the specific bioanalyte, which only is very specific to the recognition site of that enzyme, and it will form a complex of enzyme substrate complex, and there is this association constant K1. It can also have a dissociation constant K minus 1 here. So it is basically quite reversible. And from enzyme to substrate, it may react with another reagent, and then it becomes then enzyme plus product with a dissociation constant of K2. So here we see that at the end of the beginning of reaction, the enzyme stays intact alone, and at the end also it will stay intact alone as enzyme. But the substrate already changed into product. Therefore, enzyme can be used reversibly, can be used multiple times. This is the main benefit of enzyme as a biomolecule compared to other bioelement, which works more of as an affinity sensing, affinity sensor through binding only, like antibody and antigen. When they bind, they finish. They cannot be used anymore for second reaction, third reaction, etc. But enzyme can be done multiple times. So when you need application which require multiple reaction, which can monitor the reaction in real time as a function of time, then enzyme will be the best choice. The problem is, however, it is not that easy to find enzyme for all analyte. If there is enzyme, also it is not that easy to purify such enzyme from its environment. It is very microbiology. You need to purify the enzyme. You need to do, if you want to mass produce that enzyme, you do some sequencing of the peptide forming that enzyme. From there, you know the gene that code that enzyme, and then you can do genetic engineering to put the gene into a factor, transfect a factor in a bacteria, for example, to produce specific enzyme. So this requires multiple steps. It's not easy. That is why when you see the price of enzyme in the market, usually they are quite expensive. Because of the purification of enzyme, etc., it's not that cheap. And if the usage is only limited, the price is even more expensive. Glucose oxidizer is already relatively cheaper than other enzymes because it is used quite a lot, not only in the biosensor market, but also in other processing market. That is why people try to find different ways of making artificial enzyme using metallo-organic framework, for example. So the second part of the reaction can be considered as irreversible at the beginning of the reaction. So this part cannot be turned back when the reaction of product is significantly lower than the substrate concentration. In many reactions, the in vivo and in vitro concentration of the enzyme is much lower than the concentration of the substrate. So in that case, then all enzyme molecules are involved in the catalysis and they will become saturated. Yeah, that is why as I draw in the previous session, the graph of the calibration curve in a typical biosensor, usually after a while they will saturate because the amount of the enzyme itself usually is much lower than the concentration of substrate on the analyte. If you want to still have a high sensitivity at higher concentration, then you need to immobilize more enzyme onto the surface of the physical transducer. The saturation is also governed by the Michaelis-Menten equation. Yeah, this Michaelis-Menten equation relates the initial reaction V0 to the substrate concentration. Okay, this is the relationship. So this is the governed, yeah, as I drew earlier in the previous session. This is the how it is drawn. So when you are calibrating an enzyme sensor, it is best not to use linear linear regression equation. If you use linear regression, then your regression can only be used in this region only, or you may then approach it as two region. First region, and the second region is in this region, for example. But if you want to cover the whole region of sensing of calibration, then it is best to describe it as linear, as Michaelis-Menten equation like this. Yeah, with using Michaelis-Menten equation, then this is basically a asymptomatic asymptomatic curve. Yeah, it will saturate at Vmax here. Vmax. When the concentration approaches infinity, okay, so Km will be neglected compared to S here. The S will cancel each other, so V0 will be equal to Vmax. Km is the Michaelis constant. Often the experimental parameter Kcat is used, but the parameter equal to kinetic parameter K2 for the elementary reaction. This is the association constant, dissociation constant from the enzyme substrate product to become enzyme plus product. Enzyme substrate, yeah, to be complex to become enzyme plus product. Okay. So here some example of medical biosensor. Yeah, they have developed different kind of biosensor. Glucose biosensor is the most common one. We have also urea biosensor, for very important for people who have kidney problem. Lactate, and then creatinine. Creatinine also is used for people who have kidney problem. Glucose is for people who have pancreas problem. Glucose sensor. Enzyme lactate can be used for detection of, it relates to fatigue, yeah, of muscle because of the formation of lactic acid. And in general, enzyme-based biosensor employ semi-permeable membranes through which target analytes diffuse towards a solid phase immobilized enzyme compartment. The major drawback, many enzymes are inherently unstable, necessitating a packaging approach to limit the degradation of the biosensor performance. That is why you purchase, yeah, in the case of glucose biosensor, if you go to pharmaceutical, yeah, you go to Dr. Watson or Guardian, the electronic can be used many years, but the sensor itself is inside the sensor strip. Yeah, it is packaged in the vacuum encapsulation. When you open it, then it will expire within several days. You cannot use it when you open it. You have to use it immediately. Okay, because the enzyme will degrades with the surrounding, due to the surrounding humidity, temperature also. Yeah, because enzymes are inherently unstable because they are not in their natural or in their native environment, yeah, within the organism. So This Clark oxygen electrode sensor is one of the most commercially successful biosensor for aromatic glucose biosensor, using glucose oxidase. The glucose will be oxidized by glucose oxidase to become gluconic acid, and it will use oxygen to oxidize, to do the oxidation, and then it reacts with H2O to become hydrogen peroxide, the reduced mediator, the reduced mediator. So this, the H2O2 will be oxidized again to become oxygen, and the oxygen will be dissociated from the H2O2 to become oxygen and hydrogen. It become oxygen and water, okay, and the oxygen will be free again. During that process of, this one is oxidation, this one is reduction. Then there will be electron transfer, and this electron transfer can be captured using electrode. So this is how it looks like. In this is the oxygen Clark electrode oxygen sensor, basically oxygen electrode that detecting the oxygen content in the mediator. Okay. This platinum electrode, the KCl electrode, and AgAgC electrode. KCl electrolyte, it is located inside potassium chloride electrolyte, and this is the reference electrode, silver chloride, and there is a platinum electrode here in the middle, and the membrane, the enzyme can be put inside this, within this Teflon membrane. The GOD is placed very close to the surface of platinum by physical entrapment against the electrode with a piece of a dialysis membrane. So the enzyme activity will change depending on the surrounding oxygen concentration. So 5.7, this is the reaction. Glucose reacts with GOD to form gluconic acid, producing 2 electrons and 2 protons, reducing the GOD. Reduced GOD, surrounding oxygen, electrons, and protons react to form hydrogen peroxide and oxidize GOD, which is in the original form. Then this GOD can react again with more glucose. So the more glucose content, more oxygen will be consumed. This can be detected by the electrodes. Okay, so as we mentioned, when enzyme is put outside its natural environment, then there is a tendency that it will denature easily because of the heat, because of reaction with the humidity of oxygen, the surrounding oxygen. They can denature easily, and that's why when you put out a strip, glucose sensor strip from its packaging, you have to use it immediately. Cannot just put it on the atmospheric air like that. And so therefore, many of these, then rather than we use the purified enzyme sensor, why don't we use the whole microorganism? Because then the enzyme will stay intact within its natural environment. Yeah. So the direct use, and also it is lower cost compared to using purified enzyme. The direct use of microorganism to avoid separation and the purification of enzyme. Because when we purify enzyme from the bacteria, for example, not only the problem of high cost, but also the reduction of the content of the enzyme itself, or even the loss of enzyme activities during the separating and purifying process. The advantage is also complex enzyme system, coenzyme, and all the physiological function of the microorganism themselves. So we keep the enzyme to work in its natural situation, its natural condition, natural environment, with the hope that, of course, then it will remain active. The drawback, however, is, of course, then usually they are slower compared to purified enzyme sensor, because The analyte requires some time before it can react with the enzyme of interest, yeah, and then also with the other coenzyme system, and then until the effect of that reaction can be detected by the transducer outside. So this will require some time. So usually the drawback of microorganism or whole cell biosensors is they are slow in their transient response. Okay, the microorganism can be bacteria, can be fungi, archaea and protists, microscopic plant, even animals such as plankton and planarian. So they have various types of enzyme or proteins. Okay, then in a microorganism sensor is usually then we immobilize the microbial cell membranes onto the sensor, which is just like the enzyme membrane immobilized onto the enzyme sensor. The methods of immobilization or microorganisms is basically the same to the membrane, yeah, like being methods of adsorption, embedding, cross-linking, or covalent combining. However, usually covalent combination or cross-linking is rarely, they are rarely used for microorganism, whole microorganism sensor, because it's very difficult to address only the membrane, specific membrane protein here. It is just easier, much easier if you just use the whole membrane rather than using chemical to capture, to link to the specific functional group of the cell membrane, the bacterial membrane. Yeah, so we just use commonly used method is making the microorganism to adhere to specific to not synthetic membrane, right? Cellulose associated membrane, filtering paper or nylon membrane by centrifugation, filtration, combined culturing. And this is quite high, can show high sensitivity. Only the drawback, as I mentioned, is usually the time response. Okay, and using one whole microorganism, then you can detect if some analytes like pollutants, yeah, microorganism pathways activated by some analytes like pollutants, heavy metals, for example, and not only a single metal, zinc, mercury, cadmium, copper, those kind of pollutants in soil or in water. We can detect as a whole to indicate the high level pollution, for example, just using the whole cell microorganism. We do not know, we do not need to use specific reaction to detect what is due to this one specific heavy metal, the other one, etc. Okay. Okay, so this is respiratory activity of the microorganism sensor. Yeah, so microorganism, and then from here it is this is, I think, to detect oxygen, yeah, and oxygen electrode to detect the oxygen, yeah, oxygen sense oxygen in the contained within a certain environment. Then we can also measure the metabolic activity of microorganism sensor, yeah, like this. Take organic compounds and generate variety of metabolites containing electrode-active material. So we can use ammeter to measure hydrogen, the resulting hydrogen from that microorganism metabolism, formic acid, and we can measure the CO2 also from the metabolism of that organism. So here, one of the use is BOD sensor, biochemical oxygen demand. Maybe you have heard this. This is one of the commonly used sensor for in environment. Yeah, usually environmental treatment. It use bacteria as the detecting bioelement. So it consists of synthetic membrane. It immobilizes microorganism as the biological recognition element. Yeah, it measures the dissolved oxygen using a dissolved oxygen electrode. Then this is BOD sensor, principle of the ampheremetic mediated biochemical oxygen demand. Okay, so we have the microorganism, and all the organic source oxygen will be reacting with the respiratory chain within that organism. So the oxygen will then be processed in the respiratory of the organism, usually in the mitochondria, within that cell, and it will produce metabolites like carbon dioxide or water. And during this respiratory mechanism, then we can have a mediator like this, HCF. Which is HCF here is potassium hexacyanoferrat. Potassium hexacyanoferrat. As the electroactive compound for the ampherometric biosensor. Potassium hexacyanoferrat. Then this will be upon the respiratory mechanism. Yeah, this will be reduced to HCF2, and then at the electrode it will be oxidized to HCF3. And during that oxidation reaction, it will exchange electron with the electrode, and this electron can be detected. Yeah, then this will show indirectly the content of the oxygen, the biochemical oxygen demand within that environment, that water environment. Okay, are there any questions so far regarding catalytic biosensor? From all of you, anything? No question? So regarding, so mostly they consist of two types of biosensors. This is conventional biosensor, yeah. Either using enzyme, what we call as enzyme biosensor, or microorganism, like bacteria, like fungi, also plankton. And this is what we call as microorganism sensor, microorganism sensor. Okay. Only in the recent days, in recent years, people also try to develop nanoenzyme, synthetic nanoenzyme using inorganic material like metallo-organic framework to develop a structure that can function like an enzyme. So then they can make also catalytic biosensor. No questions? Okay, if no questions.